All right, hey guys. Today we're going to be doing some short notes on groundwater. So you should have picked up a notes packet a couple days ago. If for some reason you don't have it, go ahead and get up and get one. They're up in front of the classroom by the student stuff. And then after notes, you'll have a Quizmo to do on groundwater. This one is different for those of you who are usually prone to just guessing your way through it until you get them all right. That'll be really tricky to do this time around, and you'll see what I mean once you get logged in there and start working on the porosity gizmo. So I'm going to walk you through the groundwater notes. There's a copy of these notes on Canvas as well, and we're just going to kind of look at a few things about groundwater. We only spend this one set of notes on it just because it's not a huge standard for us to cover. Picture of the day is just some really cool caterpillars that look like snakes. My personal fave is this guy down here because he reminds me of a Ninja Turtle, and that's pretty awesome. So here we go. First thing, groundwater, if you didn't know, it's water that is beneath the surface. So as a kid, it kind of blew my mind that there was this massive amount of water beneath our feet in the ground. It's actually the largest freshwater reservoir for humans, so that's a big deal. It's our biggest collection of fresh water. Obviously, oceans are salt water. The Great Lakes surrounding Michigan, where I grew up, we learned a lot about those lakes because those are some of the largest lakes of freshwater collection on Earth. But all of the land combined, there's even more groundwater available to us. In terms of geology, groundwater does some pretty amazing erosion. There's some amazing things that groundwater can do that can cause both beauty and problems all at the same time. So there's a lot of it. It's our biggest freshwater reservoir, and it does some massive erosion problems. This is kind of just giving you an overall view of groundwater. If you just kind of want to look at this picture for a second. Some terms that you're going to have to know is something called unsaturated zone and the zone of saturation. Another term for unsaturated zone is aeration. I think that's what's on the vocabulary walls, the zone of aeration. And then the breaking point between the two, this is the top of the water table. So the unsaturated zone is where you have sediments and there's air between the pieces. The saturated zone has water between the pieces. So don't, in most cases, the groundwater is mixed in with sediment. So here it is, here's water table, and the top of that's called the water table. So it's not like there's this pocket and it's this perfectly free water that's flowing around in the ground. The water is mixed in with sediments. And then later on the notes, we'll look at some of these other features like springs and wells that are drastically affected by groundwater. A big term you've got to know is pore space. So groundwater, its ability to flow and everything about it is reliant on pores, so the area between materials. Some pieces, some sediments like rocks have very, very big pore spaces. Sand and clay have very small. So the amount of water that can be held has to do with the size of the particles and the variety of the sizes. If you picture in your head the type of water that we have outside here on campus, or not the type of water, I'm sorry, the type of ground, if you scooped up a big pile of dirt in your hand, you kind of want to think about what size particles am I dealing with. This is a cool picture that kind of makes us think about this. When you scoop up the ground outside, do you have big sediments, a mixture, or there's little tiny ones? So this question asks, which do you think has the largest pore spaces? Well, obviously letter A. Obviously letter A has the largest area, the largest spaces between. The big difference is how is B different from A and C? Well, B has a mixture. B is what we have outside. B is the reason the campus gets puddles 2 seconds after it starts to rain. Because you have a mixture of sediments, that makes the water, it's extremely challenging for the water to go through. Because you have big sediments, then medium size, and then little ones. So there's not a lot of pore spaces. 2 words that you have to know the difference between are porosity and permeability. So if you haven't written anything down yet, by George, write these down. Porosity is how much water sediment can hold. So this is more of an amount. How much? So this is going to be something like, I don't know, 50 grams. So porosity is how much water an amount of sediment can hold. Permeability is a completely different type of measurement. Permeability is how fast water can travel through it. So this is more likely to be a speed or a time. Porosity is how much. Permeability is how fast. In diagram 1, I can't remember if I already put this one on there for you. In diagram 1, you should have a picture of pore spaces. The size and the amount of pore spaces will determine how fast and how much water can get through a substance. So if you think about it, a pile of gravel, water's going to travel through that a whole lot faster than a pile of sand because they're little tiny pore spaces. Remember, if this little movie clip is going too fast, these notes are available on Canvas. So here's a cool picture giving a good example of permeability, or in other words, how fast water can travel through a substance. Gravel, it cruises through. Let's call this a gallon of water. It doesn't specify how much water we're talking about. Let's just say it takes a gallon of water 2 minutes to travel through gravel. That makes sense because gravel has huge pores in between it. Sand, it takes 20 minutes. So sand has lots of pores. It's very porous. It has a lot of gaps. But those pores are very small, like in letter C here. And so it takes the water 20 minutes to go through. Silt, if you recall from first semester, silt is super small. And so it has pores, but they are microscopic. So it takes the water 2 hours to get through the same amount of water, 1 gallon. Clay, in most cases, clay is impermeable, which means you can't get through it. Clay is very common, a reason that we are having trouble getting to groundwater, or it actually keeps groundwater in one spot. In this case, it took 2 days, but most of the clay layers on Earth are so thick that a hydrologist or someone who studies groundwater would call it impermeable. The water cannot get through it. Here's another picture showing the zone of aeration and the zone of saturation and the water table. I like what it shows up here at the top. So at the top it shows kind of a cross section of the zone of aeration. So there's the other word I used. The water table is that boundary between the two, and the zone of saturation. What's really cool about this picture is you can see that the water table is not stagnant, that it can actually change. It bends down towards the river and it comes back this way. Groundwater moves. That was always a very foreign thought to me. Groundwater moves. It doesn't flow as fast as a river, or doesn't move around as fast as waves in a lake, but it does move from one point to another. It moves mostly because of gravity. So gravity is going to pull it down to the lowest point possible, just as we get pulled down to the lowest point possible. Water is the same way. Water is a fluid, so it can get pulled down lower than we can. So gravity is a big reason that the water moves around. Now the water table itself, it changes depth. So sometimes the water table will be high, and then other seasons it will be low. This drastically affects those of you who live in New River or Desert Hills and you have a well. The depth of your well is going to be based on the precipitation amount we've had in the last few months, what season it is, and how the weather has been. Has it been dry? Has it been sunny? Has it been cloudy? All of these things affect how much water is able to stay and where the water table is. People who have wells, someone in your family probably keeps pretty close tabs on the water table. And seasons when we're extra dry, you might have to conserve water a little bit. You don't want to overpump your well. So the depth of the water table varies. It moves up and down, and the water flows. This is just a picture showing how the water gets pulled downward, and there's the saturated zone, and the depth of the water table changes. this is a neat picture. Just kind of soak this in for a second. So the caption at the bottom, this comes from your book, by the way. If you've been reading chapter 5, you would have seen this by now. It says the looping flow lines result from the downward pull of gravity. So gravity pulls water down, and the tendency of groundwater to move toward areas of reduced pressure. So water, if you kind of think of it, if you squish it down, it moves away from your hand. It goes away from pressure. And that's the same way it works when you come into the ground. So as groundwater, this is called recharge. When it enters the ground, it goes downward and it travels towards the area of least pressure. Well, in this case, it's a valley with a river in it. There's a lot more pressure under the mountains than there is over the freedom where the river is. So groundwater is going to travel down because of gravity, and it's going to go out, and it's going to find areas of low pressure, and that's normally going to be rivers and lakes and streams in some cases. This is a picture of a stream. I don't know why I typed that. Streams happen because water is under pressure and it's coming out. You see no lake here, there's no river here, there's no tributaries, no anything feeding this. This is strictly groundwater that has traveled through these rocks and is being pushed out at this weak part. Water will travel to areas with less pressure. So somewhere in here there's a large crevice that the water is seeping out of, causing this a seemingly random stream because there's no large body of water feeding it. Other areas of pressure release obviously are geysers. So both natural streams and geysers are areas where groundwater is being released. I'm not sure, I probably should have looked before I started recording this, if you have a picture of an aquifer in your notes. This is a very complicated picture of an aquifer. Let's see if I have another one on here. Here's an equally as complicated one. Sorry about that. Aquifers are areas where the groundwater is protected by something called an aquiclude. So these are going to be your layers of clay. So remember how I mentioned that clay is impermeable. So you have, it's a sandwich. It's a groundwater sandwich. You have clay on top, you have clay on the bottom, and you have groundwater flowing through. Aquifers are extremely important to agriculture. So somewhere in a higher elevation or different area, precipitation and infiltration feed the groundwater. So you have all these streams and rivers and tributaries coming out of the mountains. These would be your headwaters. When we think back to headwaters, this could be the Rockies, and these are the headwaters. Maybe down here somewhere is the Colorado River, and this is an aquifer that forms kind of on the path. So it either infiltrates, it becomes runoff, or it infiltrates. In this case, the infiltration is going between some clay layers, and this was an aquifer. This is protected water that is pretty much stuck here forever. So it either becomes runoff and goes down to a river somewhere, or it infiltrates and joins an aquifer somewhere. This is another picture of almost the same thing, showing a recharge area and the water traveling through two impermeable layers called aquitards. And it's just that the water's flowing. When I was a kid, I grew up in Michigan, as you know, and almost every town in Michigan has a water tower. Obviously, I didn't grow up in Blackfoot, Michigan, but it's really common for small towns to paint their water towers, to put, the high school mascot up there to the name of the town or something like that. And I always wondered what they were there for. And my dad probably explained it to me 100 times because I just didn't get it. And then finally, at some point, I think I was in about middle school, and he explained it to me, and I understood it. So there is a purpose to these. They're not just something random that is in the sky that small towns have. And this picture, also from the book, does a really good job of explaining it. So for the same reason that you have water flowing down to gravity, that applies a natural pressure. So putting water high up and then forcing it down, it creates pressure. And so small towns pump the water up into the tank, so up into the water tower tank, and they have to maintain a certain level of water up there in order to maintain a certain amount of pressure that can then get forced up to all of these houses. You want to have almost a very fine line. You can't have the pressure too high because then you'll have bursting pipes in houses. But you've got to engineer the perfect amount of pressure that keeps water flowing to all of the houses. So when someone's in their house and they turn on their knob, it comes out. In areas, real rural areas, they have issues with water pressure. Some days it drips out, and some days it comes blasting out of their shower, and it can like hurt them. And so hydrologists and mechanical engineers, there's a lot of fancy math that goes into figuring out what level those water tanks need to be in to push the water around. Just a fun fact. For those of you who have a well, I hope you know what it is. It's a hole in the ground that's dug in order to reach an aquifer. So remember, an aquifer is those protected layers. So the top and the bottom are called aquitards, and the middle is some sort of a porous sediment, maybe a sand or a gravel, and the aquifer is where the water is held. A problem that is more common than most of you would know is overpumping. So if you have a well, you probably share it, maybe with a few neighbors, and you get a set, maybe it's a weekly or a monthly allocation, and that's calculated by someone, somewhere. And if you overpump, you are screwing over your neighbors, and here's why. So here's a picture of a house with a well and then a farm with a well, and then somebody builds a new well. Someone has some new fancy-pantsy, state-of-the-art, high-capacity well and goes bonkers. They need to water their crops, causing what's called a cone of depression. This is when one jerk neighbor overpumps. And not only has he decreased the level of his water table, but obviously the water is now, it's not getting to this well, and it's not getting to this well, and these guys have dry wells, and they're pissed. They are really upset. So if you are living off of a well, I hope you have good relationships with your neighbors, and your neighbors tell you when they're going to fill up their swimming pool, because that is going to drastically affect the water table, or that level of groundwater. Subsidence is something that happens by either nature or people taking out too much water. So this is when you have a sinking of land. This is how sinkholes are caused in Florida all the time. Florida has a really high water table, like it's just a couple feet below the ground. And remember, water flows. And so if the water is flowing away from a region, that's going to create pore space that was never there before. And so that absence of water creates this huge amount of pores, and then the ground just caves in on itself. So here's a picture of a sinkhole. This is an example of water just naturally flowing away, creating too many pores, and the cement caves in. No one looks like this was okay. No one got hurt in this sinkhole. This is just crazy. So this is a very popular picture that is seen everywhere when talking about groundwater, and it was the leading reason for a lot of regulations on agriculture groundwater. So this is a real thing. 1925, that's where the land was. The land had decreased 30 feet. 30 feet. This guy's standing at where it's at in 1977. So the ground, the actual ground, used to be way up here in this valley. And over years of overpumping, agriculture and population booms, this was a big time period between 1925 and 1977. A lot had changed in the world, creating a bigger need for crops and people, that the entire elevation of this valley decreased. In the mid-'80s is when we got a lot more regulations on agriculture and their ability to pump water out of aquifers. So the region of the world we're looking at here is California. Another example of this, here's another example of the High Plains Aquifer. This is a very large aquifer that a lot of those plain states rely on for agriculture. None of these farms would exist in Kansas and Nebraska and Oklahoma without aquifers. But they have to be heavily regulated because you don't want to lose this water. You can't take it out of the aquifer faster than it's being recharged from the Rocky Mountains. Runoff and infiltration from the Rocky Mountains feed this aquifer. And if you take the water out faster than it comes in, we get problems. This is always a concern of a lot of conspiracy people who say that our aquifers are going to run dry and we're all going to starve to death because so many of America's farms rely on groundwater, which is kind of scary. But hopefully the conspiracists are wrong. Pollution is something you'll spend a lot of time on if you've signed up for environmental science for next year. Groundwater can be polluted just as easily as surface water. However, it's nearly impossible to identify and clean. It's very easy to identify a river that's been polluted. It's very challenging to identify how vast the problem is if groundwater has been polluted. So imagine having this massive aquifer, talk about a conspiracy, having this massive aquifer that is the basis for fresh water for zillions of farms that we get all of it. We get from the grocery store. All of that has come from these middle states. And somehow this gets polluted. And then it's used to build to grow our vegetables and fruits, mostly vegetables. That's a problem. Groundwater is easily polluted. Once it gets in an aquifer, it ruins it forever. If a recharge area is polluted, so if somewhere in, let's say, the mountains, if someone dumps something toxic up here, well, that's where the water is coming from in the first place. Now it goes into the aquifer and it pollutes all of that. It's a very complex chain reaction. And now you have the worst case scenario, which is contaminated aquifers. Please remember, guys, that aquifers are our greatest source of fresh water. And if something happens to them, we're in deep, deep trouble. Of course, humans are the most popular way of contamination. The things that do this the worst are things like landfills and farms. And not farms, not vegetable farms, animal farms. Pig farms, cow farms, they are the largest polluters of groundwater. They typically have, gosh, I can't think of the name right now, but they almost look like ponds, but they're like septic ponds. It's where they flush all of the feces and pee from the farms, and they keep them in these so-called sealed ponds, and they frequently get a leak. And now, or even if you think of a landfill, if a landfill starts to leak and it contaminates the groundwater, well, look, everyone in that town, it has wells going into that groundwater. And oh yeah, that groundwater also gets discharged into rivers. So a lot of environmental issues can be caused very, very quickly because of groundwater contamination. If you've ever seen the popular movie, or at least it was popular when I was growing up, it's called Erin Brockovich. That's a true story about a large chemical plant that knowingly contaminated groundwater and caused everyone in towns around it to develop all sorts of cancers because it was a chemical plant. It happens more than you would like to know. Here's a case of a contaminated well at a house. If you have a well, you have a septic tank. If you don't know what a septic tank is, it's where all your poop water goes. And they're usually maintained and they work fine. But if there was to be a leak in a septic tank, now that is going to pollute the groundwater. So as humans, we're pretty good at ruining things, and contaminating groundwater is no exception. We are really great at contaminating the groundwater, in which we rely on for so many purposes. Here's just another picture showing contamination. So it can happen from septic tanks, from sewage leaks, from farms and landfills, and any other sort of waste disposal. If you even paint, let's say you paint your bedroom, and you go outside and you wash out your paint buckets and you dump that into the ground. Paint is toxic, and you just dumped it into the ground. Humans, we pollute a lot. Now, there are natural pollutions. Radon gas is the leading cause of natural-born cancers, not man-made cancers in the world. So radon is a natural gas that occurs in the ground. It's a type of radioactive decay of rocks. You can't stop radon from happening. And if a large pocket of it comes in contact with groundwater, that's pollution. People didn't do it, nature did it, but still. So there's a lot of ways that groundwater can become polluted. And because of this, there are millions of people who do not have access to clean water. And so you always, teenagers are pretty good at asking themselves, well, why would someone drink water that is not clean? Well, when you have no choice, what are you going to do? When you're thirsty, what are you going to do? And so there are millions of humans who don't have access to clean drinking water, and that's an ongoing struggle for a lot of developing countries. And in some places, a lot of developed countries don't have enough clean drinking water. And so that's a topic that's thoroughly discussed in environmental science, and it's a depressing one, and tragic is what it is. Here's just one more picture. Just showing how fast you can pollute groundwater. The big points for today are porosity and permeability, and kind of understanding that water table can change. What you're going to work on now is the porosity Quizmo. That is on Canvas. And the big important thing is you only get one try. and you got to try it before you leave class today. So if there were any parts of the notes that you wanted to go back and look at, you can go do that on Canvas. Remember that I pushed the reading quiz until Friday, and the reading quiz is on groundwater. Section 5.9 in the book is on groundwater, and so that can be, if you haven't read it, you know who you are. If you haven't read it yet, get that read by tomorrow so you do well on your quiz. If you have any questions while you're working, please email me. I'm sorry I've been at so many trainings this week. It's just the way it fell. And I will see you when I get back tomorrow to answer your questions and solve your problems. Thanks. Have a great rest of your day.